There is a prism here. Here there is a red ray which is incident at an angle of 45 degree, but not only red ray, the green and blue, all these three color incident at the surface AC at an angle of 45 degree, right? A beam of light consisting of red, green and blue is incident on a right-angled prism as shown in the figure. The refractive index of the material of the prism for the above red, green and blue colors are 1.39, 1.44 and 1.47 respectively. What are the colors suffering total internal reflection? The pre-path. Mu equals the velocity of light in vacuum divided by velocity of light in medium, C by V. So we can replace C by nu lambda A divided by, we can replace V by nu lambda M. Good. The frequency never change when the light goes from one medium to another medium. So the frequency nu get cancelled. Mu equals lambda A by lambda M. So the refractive index is the function of wavelength, and the wavelength of red ray is more than the wavelength of green ray, which is more than the wavelength of blue ray. Obviously, we know that the refractive index for red color is less than the refractive index of the prism of green color, and which is less than the refractive index of the prism for blue color. Good. 1.39, which is less than 1.44, which is less than 1.47. This is given in the problem very clearly. So let us go for the problem. IC equals sine inverse of mu r by mu d. IC is the critical angle. So IC equals sine inverse of, we take mu r, the vacuum or the air refractive index is 1, and the denser medium, the prism refractive index is mu itself. Good. So sin IC equals 1 by mu. Here comes the very important relations, as mu is least means the critical angle will be the highest. So the critical angle for red color is more than the critical angle for green color, which is more than the critical angle for blue color. So this is the reference point. Sin 45 equal to 1 by root 2, that is equal to 1.414. If mu is less than 1.414, then the critical angle is more than 45 degree. Then if the refractive index is more than 1.414, then the critical angle is less than 45 degree. So we go for the conclusion. The critical angle for red color, which is more than 45 degree, so no total internal reflection takes place. So it passed to the next medium, whereas the critical angle for green color, which is less than 45 degree, so the green color undergo the total internal reflection. Similarly for the blue color. Good. So let us go for another alternative method. The path. Light ray has to pass from denser medium to rarer medium for total internal reflection. Then the angle of incident must be greater than the critical angle. Then the third, the critical angle IC equals sine inverse of mu r divided by mu d. So the solution. Light rays is incident normally on the surface AB, so it reaches AC without any deviation. So the angle of incidence at AC for all three colors are equal. IR equals IG equals I blue equals 45 degree. Now let us consider only red color. The critical angle for red color equals sine inverse of mu r by mu d. Let us substitute the value of mu r as 1 and mu d as 1.39, and we get ICR, the critical angle for red color is 46.1 degree. The 46.1 degree, which is greater than the angle of incident, so no total internal reflection takes place for red color. Let us go for green color. So critical angle for green color will be sine inverse of mu r by mu d. Mu d is replaced by 1.44 and we find that the critical angle for green color is 43.6 degree, which is less than the angle of incident. Good. Angle of incident is greater than the critical angle. Definitely the total internal reflection takes place. So green colors undergoes total internal reflection. So let us go for the next one. For blue color. For blue color, the critical angle equals sine inverse of mu r by mu d. Mu d is replaced by 1.47 and the critical angle for blue color, here there is an error. Blue color comes around 42.8 degree. So the critical angle is less than the angle of incident. Definitely blue color undergoes the total internal reflection. Thank you, children.